Hello. So here we go again. We're going to do another example of a hypothesis test. So I've still got the our little summary on the left, and including the different types of tests we're doing and different test statistics across the bottom here. So let's just dig in. So we've got, let's see, it's assumed that the mean systolic blood pressure is 120 millimeters of mercury. That's a measure of pressure. A study was done in Honolulu with a suspicion that blood pressure was higher among the population there. So they sampled 100 people and found an average of 130.1 millimeters of mercury with a standard deviation of 21.21. And then the question is, we want to test if this is a significantly different population with a 1% level of confidence, okay? So let's just go through our steps. We're gonna start with H naught, right? This is the thing that we assume to be true. This is the status quo, what is generally assumed to be true. In this case, it's that the mean is 120. I'm gonna keep the units off just to keep this simpler to look at. The alternative hypothesis is the thing that we are testing, the thing that the researcher believes to be true that's different than is normally thought. And in this case, it's that the mean blood pressure in this population is greater, right? There's no particular mean that they think it is. They just think that it's bigger than the general population, okay? So we've got our HA and H naught. We need to determine the distribution. So reading carefully through this, first of all, it's clear we are testing a mean. That's what our H naught and HA are about. And we are given the mean and the standard deviation of the sample. So notice this is not the standard deviation of the population, which means we should be looking at this second type. We're testing a mean where the standard deviation of the population is not known. So we compute the test statistic. Let's see. We compute, let's see, looking at this formula here, it's X bar, our sample mean, minus the mean of the population, divided by the sample deviation, which has been divided by the square root of n. So in this case, what do we have? Our sample mean is 130. 120 is the population mean. 21.21 is the sample standard deviation divided by the square root of 100. And I worked this out to be 4.762. Okay, so that is our critical, sorry, that is our test statistic. So in order to compute the to now decide what, oh, sorry, I keep forgetting to say this first, and I just want to note that alpha is 0.01. So we need to determine if we should, based on this test statistic, if we should reject or fail to reject H naught. And I'm going to use the method where I look at critical, I'm going to look at a critical t-score. In other words, similar to the critical, to the normal distribution, right? A t-student distribution looks very similar. It has the same mean. We're doing now a one-tailed test because I'm looking for, right? Our suspicion is that the mean is higher. So I'm looking for the t-score that has 0.01 area above it, okay? So in order to do this, we can use a similar operation that we have with our normal distribution. We look for an inverse calculator. So I found this inverse t-student distribution calculator. I have to put in the degrees of freedom. Remember, the degrees of freedom is 1 less than the sample size, so 99 here. I'm putting in the proportion of the area, and which is 0.01, and telling it I want a one-sided test, and it gives me back the t-score. So what this is telling me is that a t-score of 2.365 has 0.01 area above it, okay? So above this is gonna be our zone of rejection, right? Going above this score represents more extreme, more rare events, right? And remember, that's one way we think about this. We're seeing if we're having such an extremely rare event that we don't believe the assumptions it's based on, okay? So in our case, our t-score is 4.762, which is going to be significantly further along this curve, right? It's going to be almost twice as far away. So somewhere up here is our 4.762, okay? Which means, in this case, we are going to reject H naught with a 1% level of significance, right? Notice, and the other way that we do this rejection or fail to reject test is by looking at the probability. So we could certainly look at the probability of having a t-score greater than 4.762 and determine whether it's bigger or smaller than 0.01. But looking at this picture, you can see this area above 4.762 is certainly smaller than the area of all this red and that area, right? All we're doing is the red is just adding to, right? They both keep going forever. So it has to be the case that we have a smaller, this is what we sometimes call our p-value, and it's smaller than alpha, and so we reject H naught. So they're really the same thing, whether we do it by looking where it is on this graph or if we compute the probability and compare it to alpha. But in both cases, we're gonna reject with a 1% level of significance. We believe that this rare event is rare enough that it's more likely that this population has a different, in this case, higher mean blood pressure than the general population, okay? All right, thanks everybody. That is it for that one. I will see you for the next one.